Right now, standard multi-agent systems rely on rigid flowchart loops, and when these systems face uncertainty, they completely break. They get stuck in infinite tool-calling loops, stop prematurely before verifying an answer, or worse, pass errors back and forth in silent hallucination cascades. To fix this, the industry is pouring resources into making large language models internally Bayesian. The goal is having the neural network itself calculate the exact probability of its own correctness. But trying to track posterior distributions across billions of individual parameters is computationally prohibitive. Even if we could afford the compute, the uncertainty a model has about its next token doesn't actually align with the uncertainty we care about at the system level. A model can be completely uncertain about which word to generate next, while being entirely correct about the underlying semantic answer. Generating plausible text sequences is a solved problem. The actual bottleneck for agentic AI is control. The crisis is figuring out how to make robust routing, stopping, and budget allocation decisions when the available information is incomplete. We must decouple prediction from decision-making. LLMs act as non-Bayesian black box predictors. Their outputs feed into a central orchestrator as noisy sensor readings. This controller handles routing, stopping, and budget allocation. Bayesian math applies only here. Agents generate text, the controller handles the math. By shifting the mathematical burden away from the neural network and onto the control layer, we bypass the need for theoretical breakthroughs in LLM training. We can engineer systems that make Bayes-consistent decisions today. Consider a multi-agent system tasked with writing a Python function based on a natural language prompt. This graph shows the probability of a binary outcome. We call this task-level belief factoring. Instead of tracking the uncertainty of individual text tokens, we define a low-dimensional mathematical belief state for the entire task. In this case, either the generated code fails the unit tests, represented by y equals 0, or it passes them, represented by y equals 1. Before a single line of code is written, the system holds an initial prior state. This specific latent variable, y, is the only metric the orchestration layer monitors to make its next decision. As the task progresses, specialized subagents enter the workflow. A coder drafts syntax, a retrieval agent pulls reference examples, and a static safety checker scans for vulnerabilities. They each submit their outputs as discrete messages, which we label Z sub t. The orchestrator ignores the syntactic details of those messages. It evaluates the incoming data strictly against its likelihood to shift the probability curve of y. It asks one precise question. Does this new piece of evidence make it more or less likely that the code will pass the tests? Isolating the belief state to this single task-level outcome strips token-level LLM hallucinations of their impact. If an agent hallucinates a variable name, it doesn't break the system logic. It simply registers as statistical noise that lowers the probability of y equals 1. The logic driving that probability shift is the Bayesian update equation. This formula shows how the orchestrator calculates the current belief state. The prior belief is sequentially updated by multiplying it against the likelihood factor of the queried agent's message. But applying this equation exactly as written exposes a structural flaw. Large language models are trained on over-and-over internet data and share internal architectures. Their outputs are highly correlated. If you ask 3 different agents the same question, they might all give you the exact same hallucinated answer, creating an overconfident feedback loop. The mathematical countermeasure to this shared error structure is the alpha exponent. When correlated agents stack multiple false positives and cause a jagged, overconfident spike in the probability curve, the alpha exponent tempers the likelihood factor and flattens it back out.
This is the reliability weight. It acts as a tempering exponent that intentionally downweights evidence from noisy or miscalibrated agents. The system doesn't rely on a static guess for this number. It dynamically updates the alpha parameter online using an exponential weighting scheme based on that specific agent's historical log loss. If an agent consistently fails across past tasks, its reliability weight drops. Likelihood tempering acts as the system's primary safeguard. It ensures that the overall orchestrator cannot be hijacked by a single, highly confident, but factually incorrect agent. This orchestration framework extends beyond simple pass-fail conditions. Consider a live cloud system outage where the orchestrator must diagnose the incident. This chart illustrates the discrete hypothesis space, H. Instead of a binary outcome, the orchestrator tracks multiple mutually exclusive root causes. The variables are now a memory leak, a race condition, or an upstream API change. During the deliberation process, specialized diagnostic agents act as competing sensors. One parses error logs, another reviews recent code commits. As their messages arrive, the posterior distribution is mathematically pulled toward the true root cause. The controller assigns agent-specific observation models, enforcing hierarchical priors across the team. It recognizes that the log parsing agent is highly reliable when evaluating the modally weak hypothesis, but mostly uninformative when evaluating the API change. Wrapping black box text generators in a Bayesian framework provides a mechanism to aggregate conflicting evidence. It isolates the most probable truth out of a chaotic multi-agent debate. This creates a continuous flow of updated probabilities, but it raises the ultimate orchestration problem. How does the control loop know when to stop querying agents and actually execute an action? The decision to halt is governed by expected utility and value of information policies. The orchestrator executes a strict threshold logic. It will only trigger another LLM tool call if the expected mathematical improvement to the task outcome outweighs the added latency and computational dollar cost of generating that query. By operating this way, Bayes' consistent orchestration takes abstract epistemic uncertainty and transforms it directly into a measurable economic trade-off. Managing this economic trade-off across a long-horizon multi-agent interaction inevitably runs into hardware limits. Eventually, you run out of context window. The solution to this scaling issue is belief state distillation. Instead of feeding thousands of tokens back into an LLM context window for every step, the system relies on the Bayesian posterior. That probability distribution serves as a highly compressed, low-memory sufficient statistic of every past exchange. This graphic lists the explicit design patterns required for Bayesian orchestration in production. Notice the emphasis on task-level belief factoring and belief state distillation. By treating human feedback, tool outputs, and LLM text entirely as probabilistic observations, the system discards the raw text after updating the math. The architecture scales smoothly without ever hitting a context limit. There is a strict operational limit to this framework. If multiple agents share the same pre-training data or prompt structures, their outputs will correlate. To avoid generating false certainty, evidence pooling in the orchestration layer must remain heavily tempered and intentionally conservative. The race to build better sequence predictors will continue, yielding larger and faster text generators. But generating text is not the same as taking action. The future of high-stakes agentic AI belongs strictly to systems engineered from the top down as coherent decision-makers under uncertainty.